Imagine atoms as individuals seeking stability and fulfillment through companionship. Like people, atoms can achieve this by forming bonds with one another, sharing or transferring electrons to achieve a more stable state. Let's consider the classic example of water, H2O. In water, two hydrogen atoms and one oxygen atom come together through covalent bonds. Oxygen, with its higher electronegativity, attracts the shared electrons more strongly, creating a partial negative charge near the oxygen atom and a partial positive charge near the hydrogen atoms. This gives water its unique properties, such as surface tension and the ability to dissolve a wide range of substances. Now that you have a little idea, let us guide you through the depths of chemical bonding. I am Dina Silvar from Team Gadolinium with my groupmates Ron Vincent Fabian, Janamo Pusti, Peaches Martinez, and Natalie Cole Tripon, and we will be discussing about chemical bonding. Specifically, we will tackle different theories and concepts behind chemical bonding, and we will discuss the following subtopics. First is the valence shell electron pair repulsion or VESPER theory, and we will use it to predict the molecular and electron geometry of different compounds. Next, we will tackle another theory that revolves around molecular geometry, which is valence bond theory. And lastly, we will talk about the molecular orbital theory to see beyond how diatomic molecules bond.
Molecular geometry, also known as the molecular structure, is the three-dimensional structure or arrangement of atoms in a molecule. But before we tackle this topic, we should recall these three important subtopics when making molecular structure, which is Lewis electron dot structure, bond angles, and valence shell electron pair repulsion. Lewis electron dot diagrams. In 1916, Gilbert Lewis Newton introduced a simple way to show the bonding between atoms in a molecule through Lewis electron dot diagram. In this diagram, we are required to count the valence electron on each atom, and these valence electrons are represented as dots. When two pairs of electrons are paired, they are called lone pairs, and they are located on the atom adjacent to each other. And when two paired electrons are shared between each atoms, they are called bonds, and they are shown as lines. This is the flowchart for logic involved in Lewis dot structure technique. We can use this flowchart as a guide when making Lewis dot structure, or we can follow the steps in the next slides that further explain this technique. In this chart, we can see that the first step is to count the available valence electron, or AE, and then we draw the hypothetical structure and count the number of hypothetical electrons in the structure. The third step is to compare the actual electron or available electron and the hypothetical electrons. If the hypothetical electron is equals to the available electron, then the hypothetical structure is the Lewis structure. If the hypothetical electrons is less than the actual electrons, then we can have the expanded octet. And if the hypothetical electron is greater than the actual electron, or the available electron, we will ask if the atom can have less than octet or 8 electrons. If yes, then the Lewis structure has less than octet. If no, the Lewis structure has resonance structures. Steps in Lewis dot structure techniques. The first step is to determine the total number of available valence electron. In this step, we determine the total number of valence electron available. Each atoms of the available representative elements contribute the number of electrons equal to its group number. For example, 1A, 1 electron, 2A, 2 electrons, or 2 valence electrons, to 7A. If there is an odd number of electrons, the structure will be free radical, which has a lone electron in an orbital. This electron will exist in a non-bonding orbital or multiple band. If the compound is an ion, add 1 electron for each negative charge and subtract 1 for each positive charge. Next is to determine the structural connectivity. First is the central atom. The central atom is usually the least electronegative elements in the compound, and hydrogen and halogens are almost always connected to only one other atoms, so they are usually terminal rather than central. Another clue is that chemists usually list the central atom first in the chemical formula, such as CCl4 and CO2. The next is to draw the hypothetical structure with each atom surrounded by 8 electrons in pairs, or we call it octet. In here, we place two electrons forming a single bond between bonded atoms by drawing a line between the two atoms. For each atom not surrounded by an octet of electrons, or 4 bonds, add lone pairs of electrons, or 2 dots to a lone pair. We do that until all atoms are surrounded by an octet. We can note here that hydrogen can only have 2 valence electrons. The fourth step is to count the total number of electrons in the hypothetical structure. If it's equal to the number of available electrons from step 1, then this is the correct Lewis dot structure. If it's greater, then we proceed to step 5. If it's less, then we go to step 7. The step 5 is to determine if atoms can have less than octet, like hydrogen that can only have 2, and group 2A that can have quartet or 4 electrons, and group 3A that can have sextet or 6 electrons. If not, then proceed to step 6. If so, then decrease the number of lone pairs around these atoms until this number of electrons in the structure is equals to the number from step 1. The sixth step is to combine adjacent lone pairs into multiple bonds. We place multiple bonds into structure by replacing two lone pairs from two adjacent atoms with a bonding pair. And we can repeat this until the structure has the same number of electrons as the step 1. The seventh step is the expanded octets. If any atoms have d orbitals available, they can have expanded octet or greater than 8 valence electron. We can add lone pairs to these atoms until the number of electrons is equals to the number from the step 1. The eighth step is resonance structure. We can check the step 6 to see if there's an additional electron configuration that can be drawn by changing the position of multiple bands. This changing of positions of multiple bands represent resonance structure. The best configuration will typically be the ones where the atoms are assigned the formal charge closest to zero. And the ninth step is the formal charges. These correlate the electron location in the molecule to the atom that donates them. We can use the formula formal charge is equals to valence electron minus the non-bonding valence electron minus the bonding electron over 2. Bond angles. Bond angles are the angles between adjacent lines representing bonds. You can see here that bond angles contribute to the shape of the molecules. It can also help differentiate between linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. It also says here that the ideal bond angles are the angles that demonstrate the maximum angle, where it would minimize the repulsion, and verifying the best pair theory. Bond angles and Weisser theory. The Weisser theory, or the valence shell electron pair repulsion theory, is used to study the bond angles. The angle between the adjacent bond defines the bond angle. And according to this theory, the lone pairs in the valence shell of the central atom will arrange themselves to minimize the repulsion and maximize the distance between them. And as a result of this, the molecules will form a regular geometric shape. Bond angles and molecular shape. The Weisser theory predicts the five fundamental shapes of molecules with no lone pairs. And bond angles can distinguish these five shapes. We can see here with 180 degrees bond angle is called linear, and the one with 120 degrees is called trigonal planar, and with 109.5 degrees bond angle is called tetrahedral, and the one with 120 degrees and 90 degrees band angles are called trigonal bipyramidal, and the one with 90 degrees in all of its band angle is called octahedral. Now that we know the five fundamental shapes of molecules with no lone pairs, we can proceed to the effect of lone pairs on band angle. Lone pairs of electron on the central atom affect the molecular shape. The lone pairs are located in the atomic orbitals of the central atom and repel the band pairs, causing a deviation from their geometry. Therefore, the band angles of some molecules depend on the number of lone pairs. Here an example: tetrahedral methane with 4 band pairs has a band angle of 109.5 degrees, and ammonia with 3 band pairs and 1 lone pair, which has only a band angle of 107.5 degrees. We can see here how the lone pair repels the band pair because the lone pair has higher repulsion energy than the band pair. Another one is water with 2 band pairs and 2 lone pairs. And again, we see a decrease in the band angle, which only now becomes 104.5 degrees. Valence shell electron pair repulsion theory, first presented by Sidgwick and Powell in 1940, which states that electron pairs repel each other whether or not they are in band pairs or in lone pairs. Thus, electron pairs will spread themselves as far from each other as possible to minimize the repulsion, which makes sense because electron pairs are negatively charged particle, and two negative charge will create repulsion from each other. Christopher theory postulates that polyatomic molecules consist of three or more atoms, with one central atom linked to all the other atoms within the molecule. Next is the total number of valence shell electron pairs decide the shape of the molecule. And the electron pairs tend to align themselves to minimize the electron-electron repulsion and maximize the distance between them. The valence shell is a sphere where electron pairs are positioned on the surface to maximize their distance. The molecule can be expected to have an asymmetrical shape if the central atom is surrounded by electron band pairs. The Weisser theory can be applied to each resonance structure of a molecule, indicating that a distorted shape is likely when the central atom is surrounded by both lone and band pairs, and the repulsion strength is highest in two lone pairs and weakest in two band pairs. The proximity of electron pairs around the central atom lead to their repellency, resulting in an increase of energy in molecule. The distance between electron pairs decreases their repulsion, leading to a decrease in the molecular energy. Vesper theory limitations. The Vesper theory is limited in explaining isoelectronic species, transitional metal compounds, and halides of group 2 elements. It also does not accurately describe the structure of these compounds due to insufficient consideration of substituent group sizes and inactive lone pairs. It predicts a linear structure for halides of group 2 elements, which is actually a bent one. In this table, you can see different molecular geometry or shapes. First is the five fundamental shapes with no lone pairs, which is linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Next is trigonal planar with one lone pair is called bent, and the tetrahedral with one lone pair is trigonal pyramidal, and with two lone pair is another bent. A trigonal bipyramidal with one lone pair is called sawhorse, and one with two lone pairs is called T-shape, and with three lone pairs is called linear. For octahedral with one lone pair is called square pyramidal, with two lone pairs is called square planar, three lone pair is called T-shape, and four lone pairs is linear. Rules for predicting molecular structure using Vesper model. First is two pairs of electrons on a central atom in a molecule are always placed 180 degrees apart. It adheres to the Vesper theory postulates that electron pairs tend to align themselves to minimize electron-electron repulsion and maximize the distance between them. In the case of two pairs of electrons, the maximized distance or maximum distance between them that minimize the repulsion is 180 degrees. Second is three pairs of electrons on a central atom in a molecule are always placed 120 degrees apart on the same plane as the central atom. Of course, if there's a lone pair, the distance between the bonding pairs will decrease and the distance between the lone pair and the bonding pair will increase. The third is four pairs of electrons on a central atom in a molecule are always placed 109.5 degrees apart. And again, if there's a lone pair or there are lone pairs, then the distance between the bonding pairs will decrease. Let's try determining the geometric structure of H2O and CO2 with these four steps. First, draw the Lewis structure. Next is count the electron pairs and arrange them in a way to reduce the repulsion. For H2O, 4 electron pairs, and CO2, 2 electron pairs. Third is to determine the position of the atoms from the way the electron pairs are shared. For H2O with 2 bonding electrons and 2 non-bonding electrons, pushing the bond angle to 104.5 degrees. And CO2 for 2 bonding electrons is equals to 180 degrees. Last is to determine the name of the molecular structure from the position of the atoms. From H2O, we can see it is a tetrahedral with 2 lone pairs, and the tetrahedral with 2 lone pairs is called bent. And for CO2 is 2 pairs of electron on a central atom is called linear.
The valence band theory is one of the quantum mechanical theories used to describe covalent bond formation in the electronic structure of molecules. It is pivotal to underscore that valence band theory is tailored specifically for understanding covalent bonds and doesn't extend its scope to elucidating phenomena such as ionic or metallic bonding. A fundamental principle of valence bond theory states that the electrons in a molecule occupy atomic orbitals of the individual atoms, thereby preserving a distinct reflection of the contribution of individual atoms to the bond formation. Moreover, it furnishes valuable information on key parameters such as bond energy, bond length, overlapping orbitals, and a molecule's shape. The valence bond theory explains that a covalent bond is formed by the overlapping of atomic orbitals of two atoms. Consider the formation of an H2 molecule from two H atoms. According to the principles of valence bond theory, the formation of the covalent bond between two hydrogen atoms, known as the HH bond, occurs through the interaction and merging of their respective 1s atomic orbitals. This emerging, referred to as overlap, signifies the sharing of a mutual space within the orbitals, which is called the overlapping region, which has the maximum density of electrons. And in simpler terms, the valence bond theory suggests that the hydrogen atoms come together and their 1s orbitals combine in such a way that they occupy the same area in space, facilitating the creation of the HH bond as illustrated in the figure shown. And as two hydrogen atoms approach each other and initiate bond formation, a pertinent question arises. What precisely occurs during this process of bond formation between the two atoms? Initially, when the two atoms are situated at a distance from each other, there is no interaction between them, resulting in zero potential energy for the system composed of the two hydrogen atoms. However, as the atoms draw closer, each electron in one atom becomes attracted to the nucleus of the other, while simultaneously experiencing repulsion from the other electron and nuclei. Despite the repulsion, the attraction between the electrons and nuclei prevails when the atoms are still separated, causing a decrease in the system's potential energy, rendering it negative as the atoms approach. This trend persists until the potential energy reaches its minimum value, signifying the system's maximum stability. This state corresponds to a significant overlap of the 1s orbitals, leading to the formation of a stable H2 molecule. Further reduction in the distance between the nuclei results in a steep rise in potential energy, driven by increased electron-electron and nuclear-nuclear repulsions, eventually yielding a positive potential energy. And according to the law of conservation of energy, the reduction in potential energy during H2 formation must be accompanied by the release of energy, as evidenced by the experimental observations where heat is emitted as an H2 molecule is formed from two H atoms, and conversely, to break a HH bond, energy input is required. Thus, the valence bond theory states that a stable molecule results from the interaction of reacting atoms when the potential energy of the system has reached its lowest point, representing a minimum value. And for atomic orbitals overlapping, it is the process in which the two atoms come so close to each other that they penetrate each other's orbital and form a new hybridized orbital where the bonding pair of electrons reside. These hybridized orbitals has lower energy than the atomic orbital, making it more stable. In addition, when two atoms approach each other for bond formation, the nature of their overlap can vary, being positive, negative, or even zero. This variability is dependent upon the pace and sign of the interacting orbitals involved in the bonding process. Here are the three natures of atomic orbitals overlapping. First is the positive overlapping of atomic orbitals. It is when the pace of two interacting orbitals aligns, resulting in both having the same sign. The overlap is deemed positive, facilitating bond formation. It's essential to note that the pace of these orbitals, denoted by either positive or negative values, stems directly from the sign of the orbital wave function and isn't correlated with the charge in any manner. Meanwhile, when the pace of two interacting atomic orbitals contrast, indicating opposite signs, the resultant overlap is negative, impeding band formation. And lastly is when the orientation of two interacting atomic orbitals is such that they do not overlap at all. This condition is termed zero overlapping. According to the valence bond theory, it is imperative to note that the spin of electrons in overlapping orbitals must be opposite for the formation of a covalent bond. These overlap orbitals retain their identity but with lower energy levels compared to their states before overlapping. In addition, it is asserted that the overlapping of atomic orbitals must occur at an optimal or favorable position for the formation of a stable covalent bond. Moreover, the degree of overlap between these orbitals plays a crucial role in determining key properties of the band, including its energy, strength, and length. Specifically, the extent of orbital overlap directly influences the band strength and energy, with greater overlap corresponding to stronger bands and higher band energies. This emphasizes how critical it is for the precise alignment and extent of overlap between atomic orbitals to determine the specific characteristics and overall stability of covalent bonds within molecules, as proposed by the valence bond theory. The overlap between atomic orbitals can occur in two primary orientations, axial and parallel. Axial overlapping, also referred to as head-on collision, where the orbitals align along their axes. In this configuration, a sigma bond is formed. Conversely, parallel overlapping involves the alignment of orbitals side by side. Unlike axial overlapping, parallel overlap exclusively results in the formation of a pi bond. This distinction in overlapping orientations underscores the diverse nature of sigma and pi bonds in covalent molecular structures. The sigma and pi bonds provide valuable insights into the bond energy, strength, and length of a molecule. It's important to remember that a sigma bond always involves maximum overlapping, while a pi bond entails minimum overlapping. Valence bond theory asserts that the degree of overlapping directly determines the strength, energy, and length of the bond. Consequently, sigma bonds tend to be stronger than pi bonds due to their greater degree of overlapping. The significant overlapping in a sigma bond enhances the bond strength and energy of the molecule, whereas the minimal overlapping in a pi bond reduces both bond strength and energy. The order of increasing bond energy and strength among various combinations of atomic orbitals follows a specific pattern as shown here.
Now, let us discuss hybridization. Hybridization is the combining of atomic orbitals to make hybrid orbitals and redistribute the energy of individual atoms to give orbitals of equivalent energy. Hybridization is crucial because it helps explain the shapes and bonding of molecules. By mixing atomic orbitals to form hybrid orbitals, it provides a more accurate model for understanding molecular geometry and bond angles, which are essential for predicting the properties and reactivities of molecules. Generally, we can classify the type of hybridization by combining the number of atoms bonded to the central atom and the number of molecules. The process of hybridization includes the promotion of electrons from ground state to excited state and forming the hybridized orbital. There are different types of hybridization. The five common hybridization includes sp, sp2, sp3, sp3d, sp3d2 hybridized orbitals. So let us define each type. Sp hybridized. This type of hybridization is linear in structure, having a 180-degree bond angle. The 2s orbital and 2p orbital hybridize to form two sp orbitals. Each of them consists of 50% s character and 50% p character. sp2 hybridized. For this type, it has a trigonal planar molecular geometry with 120-degree bond angle. The 1s orbital and p orbital hybridize, creating three new hybrid orbitals. The s character for this hybrid orbital is 33% and 67% for p character. sp3 hybridization. It refers to the mixing of one s orbital and three p orbitals to form four equivalent hybrid orbitals. These hybrid orbitals have a tetrahedral arrangement and are utilized by atoms to form covalent bonds in molecules. This hybridization occurs in molecules where a central atom is bonded to four other atoms or lone pairs, resulting in a geometry with bond angles of approximately 109.5 degrees. One example for this type is methane. Relatively, it has 25% S character and 75% P character. sp3d hybridized. This involves the combining of one s orbital, three p orbitals, and one d orbital to form five equivalent hybrid orbitals. The molecular geometry of this type is trigonal bipyramidal geometry, with three orbitals arranged in an equatorial plane and two in axial positions. This hybridization occurs in molecules where a central atom is bonded to five other atoms or lone pairs. One example of compound exhibiting sp3d hybridization include phosphorus pentachloride. This type has S, P, and D character having 20%, 60%, and 20% respectively. sp3d2 hybridized. This involves the mixing of one s orbital, three p orbitals, and two d orbitals to form six equivalent hybrid orbitals. These hybrid orbitals have an octahedral arrangement with four orbitals arranged in an equatorial plane and two in axial positions. This hybridization occurs in molecules where a central atom is bonded to six other atoms or lone pairs. For this type, S character is 17%, P character is 50%, and D character is 33%. Note, in computing the percentage characters, divide the number of energy level present to the total energy levels present and multiply it to 100. Here are the examples for each type of hybridization. We have beryllium chloride for Sp, boron trichloride for Sp2, methane for Sp3, phosphorus pentachloride for Sp3d, and sulfur hexafluoride for Sp3d2. In determining the type of hybridization in molecules having double and triple bonds, we should only count them as one instead of two or three. Alkene is one example of molecules that has double bonds, but despite having multiple bonds, they are mostly classified under sp2 hybridization. Here is an example problem that you can answer on your own. There are multiple possible type of hybridization present for this molecule. Stop the video if you need time for answering. The answer key will be shown in a while.
Now that you have some idea about hybridization and how it is used to predict the stability, reactivity, and shape of the molecules, let us delve into the diatomic molecules and how specifically they form bonds. So, molecular orbital theory, or simply known as MOT or MO theory, explains phenomena such as paramagnetism in covalent molecules or why certain species form unstable compounds. More specifically, in MO theory, the atomic orbitals on individual atoms combine to produce new molecular bonds that give rise to bonding and antibonding orbitals that exist between nuclei. Before I discuss more about molecular orbital theory, let us first talk about its advantages over VSEPR and valence bond theory. First is MO does a good job of predicting electronic spectra and paramagnetism, when VSEPR and valence bond theories do not. The MO theory, like valence bond theory, predicts the bond order of molecules, however, it does not need resonance structures to describe molecules. Third is the MO theory treats molecular bonds as a sharing of electrons between nuclei, unlike the valence bond theory, which treats the electrons as localized hybrid orbitals of electron density. Fourth is MO theory says that the electrons are delocalized, which means that they are spread out over the entire molecule. And lastly, MO theories can be used to describe bonds between the atomic molecules. Now, let us discuss what MO theory is really all about. In MOT, when two atoms come together, their atomic orbitals interact to form two possible molecular orbitals. First is the lower energy or bonding MO, and second is the higher energy or antibonding MO. The lower energy MO stabilizes the molecule, while the higher energy antibonding MO destabilizes the molecule. As shown in the figure in the slide, the energy difference between the sigma and sigma star molecular orbitals is significantly greater than the difference between the two pi and pi star sets. The reason for this is that the atomic orbital overlap and the strength of the interaction are greater for a sigma bond than a pi bond, which means that the sigma molecular orbital is more stable or lower in energy than the pi molecular orbitals. For an instance, in a diatomic hydrogen molecule, when one s orbital of each H atom subtract, antibonding orbital forms. When one s orbital of each H atom add, a bonding orbital forms. At higher energies, one s orbitals form destructive interactions to form antibonding orbitals, while at lower energies, one s orbitals form constructive interactions to form bonding orbitals.
So in these sections, we will discuss the molecular orbital configuration and the localization. So defining the molecular orbital configuration describes how the electrons are distributed among the molecular orbitals of a molecule. These molecular orbitals are formed by the overlap of the atomic orbitals from the constituent atoms. So in this case, we must get first familiarized with the rules governing the molecular electron configuration and the stability before we delve deeper. In order to write the electron configuration of a molecules, we must first arrange the molecular orbitals in order of increasing energy. Then we can use the following guidelines to fill the molecular orbitals with electrons. Then the rules also help us to understand the stabilities of the molecular orbitals. So here are the six rules. First, the number of molecular orbitals formed is always equal to the number of the atomic orbitals combined. Number two, the more stable the bonding molecular orbital, the less stable the corresponding antibonding MO. Third, the filling of the MO proceeds from low to high energy. In a stable molecule, the number of electrons in bonding MO is always greater than the antibonding MO because we place the electron first in the lower energy bonding MO. For the fourth, like an atomic orbital, each molecular orbitals can accommodate up to two electrons with opposite spin in accordance with the Pauli's exclusion principle. Fifth, when the electrons are added to the molecular orbital of the same energy, the most stable arrangement is predicted by Hund's rule. That is, the electrons enter the molecular orbitals with parallel spins. And lastly, number 6, the number of electrons in the MO is equal to the sum of all the electrons on the bonding atoms. In this example, we will use the hydrogen molecule as, uh, as to visualize further on how these rules will implemented. So first, let's list the electron configuration of hydrogen, which is 1s1. Then, since it is a molecule, we will put each hydrogen on both sides to fill in the 1s level, which contains one electron on the left side and on the right side. Thus, this total of this electron would be added, and then it will fill up this the bonding molecular orbital sigma 1s, which resulting to a two electrons or a pair of electrons. For the helium, since it has a 1s2 configuration, we will fill in the 1s level of two electrons each, and then each electrons would be distributed to the two uh, molecular orbital of the bonding and the anti-bonding, which resulted to an overall of four electrons and two in each anti-bonding molecular orbital and two for the bonding molecular orbital. So now, what does it mean if there's an electrons in the anti-bonding orbitals and in the bonding orbitals? So let Na be the number of electrons in anti-bonding orbitals and Nb be the number of electrons in bonding orbitals. And if the number of electrons in bonding orbitals is greater than the number of electrons in antibonding orbitals, it means it is stable. And that is the only situation where the molecule is stable. Thus, in any other condition wherein it's both equal, or if the electrons in antibonding orbitals is greater, then it means that the molecule is unstable. So now, to further evaluate, we will use the bond order to establish or to see or to compute how stable the hydrogen and then the helium. So for the bond order, it has a formula of 1/2 times the quantity of the electrons in the bonding MO, and the minus the number of electrons in anti-bonding MO. So for hydrogen, it has a bond order, which means it is stable, and for He, it has 0, which means it is unstable. So now, going for the more complicated part, in which the bonding involves the p orbitals, and these two p orbitals form either a sigma bond or a pi bond. That because there are three p orbitals for each atom of the second period element. So now, that one sigma and two pi molecular orbital will result from the constructive interaction. In here is the summary of the increasing order of the molecular orbital energy, in which showcases the comparison of uh, which level contains a higher energy than the other. So in this example, the carbon molecule has the configuration of 1s2, 2s2, and 2p2, which has 12 electrons in the C2 molecules. Therefore, uh, this result into the electron configuration of the two electrons in in the bonding sigma 1s, and then antibonding in the 1s level, and then the bonding sigma in 2s level, um, two electrons on the bonding sigma level, and then two electrons in each pi 2p level of the carbon. Using the bond order computation, it results to a 2, which means that it is stable and the molecule has no unpaired electrons. Then it means that C2 is a diamagnetic molecules and it can only be detected in uh, the diamagnetic C2 molecules had been detected in the vapor state. Note that the double bond in C2 are both pi bonds because of the 4 electrons in 2 pi molecular orbitals. In most other molecules, a double bond is made up of sigma bond and a pi bond. So for oxygen molecules, we will use the ground state electron configuration of 1s2, 2s2, and 2p4, resulting to a 16 uh, electrons, and in which it occupies the 2p orbital, and it shows a unpaired electrons at the higher level of the antibonding in pi 2p. And according to Hunt's rule, the last two electrons that enters that area or that orbitals has a parallel spin, which and also it ignores the sigma 1s and the sigma 2s orbitals because their net effects on the bonding is zero. Thus, we calculate the bond order results to a 2 bond order. Therefore, O2 molecule is a paramagnetic and a stable molecule. So in this slide, it shows the summary of the second period element that showcase the bond order, bond length, enthalpy, and the magnetic properties of these uh, elements. So now for the delocalized molecular orbital, uh, it is also called as DMO, is an orbital in a molecule where electrons are not confined in a specific region between two atoms, but are uh, spread out or distributed over the multiple atoms. This typically occurs in molecules with conjugated system, where the alternating single and multiple bonds create a continuous network of the overlapping atomic orbitals. So now we will use the benzene as an example. Then benzene is a C6H6 planar hexagonal molecule with the carbon atoms situated at the six corners. All the carbon-to-carbon bonds are equal in length and strength. All the carbon-hydrogen bonds, the CCC, HCC angles, are all 120 degrees. Therefore, each carbon atom is sp2 hybridized. It forms three sigma bonds with two adjacent carbon atoms and a hydrogen atom. This arrangement leaves unhybridized two pz orbitals on each carbon atom, perpendicular to the plane of the benzene molecule or the benzene ring. Thus, this description is very similar to the configuration of the ethylene. Well, except in this case, wherein the six hybridized 2pc orbitals is in the cyclic arrangement. Because of the similar shape and orientation, each 2pc orbital overlaps two others on one each adjacent carbon atom. Thus, the interaction of the six 2pc orbitals lead to the formation of the six pi orbitals, of which three are bonding and three are anti-bonding. A benzene molecule in the ground state therefore has 6 electrons in the 3 pi bonding molecular orbital, 2 electrons with pair spin in each orbital. Unlike the pi bonding molecular orbitals in ethylene, those in benzene formed a delocalized molecular orbital, in which, as stated earlier, uh, these are the electrons are not confined between two adjacent bonding atoms, but actually extend over three or more atoms. Therefore, electrons residing any of these uh, freely moves around the ring. Thus, for this reason, it creates another representation of the benzene with a ring inside. that indicates that the pi bonds between the carbon atoms are not confined to any individual pairs of the atoms. Rather, the pi electron densities are evenly distributed throughout the benzene molecule. Then the carbon and hydrogen atoms are not shown in the simplified diagram. So now that we can state that each carbon-to-carbon linkage in benzene contains a sigma bond and a partial pi bond. Thus, the bond order between any two adjacent carbon atoms is therefore between 1 and 2. Carbonate ion is another example of cyclic compounds with delocalized molecular orbitals. The VESPR predicts a trigonal planar geometry for the carbonate ion, similarly to the boron trifluoride. The planar structure of the carbonate ion can be explained by assuming that the carbon atom is sp2 hybridized. The C atoms form sigma bonds with three O atoms, thus the unhybridized 2p-C orbitals of the C atoms can simultaneously overlap the 2p-Z orbitals of all O atoms. The result is a delocalized molecular orbital that extend over all four nuclei in such way that the electron densities in the carbon-to oxygen bonds are the same. Therefore, the MOT provides an acceptable alternative explanation of the properties of the carbonate ion as compared with the resonance structure of the ion. We should also note that the molecules with the localized molecular orbitals are generally more stable than those containing molecular orbitals extending over only two atoms. Such one example is the benzene molecules that contain the localized molecular orbital is chemically less reactive but more stable than uh, molecules containing localized C to C double bonds, such as the ethylene.